Welcome to this comprehensive analysis. Please note that this is an AI-generated analysis.
Right. It's always good to state that clearly up front.
Exactly. So, to kick things off, I want you to imagine your company implements, a brilliant artificial intelligence chatbot.
Okay. A pretty standard scenario these days.
Right. And a customer asks it for a clothing recommendation, and the
hmm
chatbot confidently suggests this beautiful blue sweater.
Sounds great so far.
It does, but then the customer clicks a link only to discover the sweater has actually been out of stock for 3 days.
Oh, yeah. That is incredibly frustrating for a user.
It really is. And this scenario happens constantly because, well, the artificial intelligence database and the transactional database operate on entirely separate servers.
Exactly. They are completely disconnected.
So today, we're conducting a detailed technical review of AI-ready PostgreSQL 8.2.
Yes, and it's a fascinating subject.
Our mission here is to examine how this specific software serves as a unified data platform. We want to look at how it handles high-volume transactions, complex analytics, and artificial intelligence workloads.
And doing all of that without the need for those fragmented multi-database architectures we just talked about.
Right. So my foundational question for you is, why did the software industry historically rely on entirely separate databases for these tasks in the first place? I mean, how does PostgreSQL break this historical limitation?
Well, historically, hardware limitations really forced architects to use specialty databases. I mean, each workload requires vastly different physical operations.
How so?
Well, transactional databases, they optimize for finding and updating a single row instantly.
Right, like a single customer checkout.
Exactly. But analytical databases, they optimize for reading millions of rows to generate massive summaries.
I see. And AI is different from both.
Very different. Artificial intelligence requires mathematical distance calculations across thousands of dimensions.
Wow, okay. That's a lot of computing.
It is. However, PostgreSQL utilizes a unique object relational architecture, and this design allows the database to act as an extensible framework.
Extensible, meaning it can just keep adding new capabilities.
Precisely. It can adopt entirely new data types like mathematical vectors and process them all under a single, reliable transactional umbrella.
So you don't need to build, brittle pipelines to move data between specialty systems anymore.
Right, no more duct taping systems together.
We can kind of think of the traditional multi-database approach like a global supply chain where parts are shipped across oceans to be assembled.
That's a great analogy.
The parts must travel long distances, causing synchronization delays and, increasing the risk of lost items.
Which leads to the out-of-stock sweater problem.
Exactly.
Yeah,
In contrast, the PostgreSQL 18 approach operates more like a highly efficient single-roof mega factory.
I like that. Everything happens in one place.
The source material provides a sample e-commerce application to demonstrate this. The application includes an East Coast database, a West Coast database, a central analytics database, and an artificial intelligence database.
Right, a very realistic modern setup.
And instead of relying on some clunky third-party tool to copy data overnight, these microservices communicate seamlessly using PostgreSQL native features.
Yes, they primarily use logical replication and foreign data wrappers.
Right. So tell us about logical replication.
Well, logical replication is the mechanism that eliminates those shipping delays in your factory analogy.
Okay, how does it do that physically?
Instead of constantly querying the database for changes, which is slow, logical replication simply reads the database's internal diary.
The internal diary.
Yes, it's known as the write-ahead log. It then pushes those changes automatically to the central analytics database in near real time.
Oh, wow. So it operates at the storage level without needing external pipeline software.
Exactly. And then you have foreign data wrappers, which allow one database to query another database as if the remote tables were actually stored locally.
I see. So you maintain one single source of truth while securely distributing the processing load across different servers.
You got it.
Well, I have to challenge this architectural concept immediately.
All right, Ham.
Doesn't moving logic directly into the database recreate the rigid, monolithic architectures we spent the last decade trying to escape?
I hear that concern a lot.
I mean, putting business logic into the database sounds like a return to the inflexible systems of the past.
It sounds like it, but it actually avoids becoming a monolith through a modern microservices API schema approach.
Okay, explain that.
In this design, the database exposes a secure, versioned application programming interface directly through database schemas.
So the database itself has an API.
Yes. The application code only interacts with specific functions and views defined in this API. It never touches the underlying tables
Oh,
directly.
I see. The database encapsulates the business logic securely.
Right. And this maintains the agility of the development team because they can deploy new versions of the API schema without breaking the underlying application code.
Okay, that structural separation makes sense. Now, let us pivot to the mechanical reality of running high-volume systems.
The fun stuff.
Right. When hundreds of users purchase items simultaneously, the database must isolate their actions. We know about basic isolation levels, but how does balancing, say, read committed, repeatable read, and serializable levels become uniquely critical when we introduce AI workloads into the same environment?
It becomes incredibly critical because artificial intelligence operations, such as generating embeddings, are computationally very heavy.
Okay.
Read committed ensures a query only sees data committed before it began. Serializable, on the other hand, forces concurrent transactions to execute as if they occurred one after the other.
Strictly sequential.
Exactly. Now, if you apply strict serializable isolation to a long-running artificial intelligence vector update,
You'll lock out your standard checkout transactions.
precisely, you will freeze your customers out. Therefore, you must carefully assign lower isolation levels to your analytical reads, reserving strict isolation solely for financial transactions.
That is a crucial balance.
It really is. Furthermore, to maintain performance, you must manage your data history carefully. The text details using slowly changing dimensions, specifically type 6.
Right, type 6. Instead of creating a new row every time a product category shifts, type 6 stores the current value, the historical value, and the valid date ranges within the exact same row.
Yes, which makes querying historical states much more efficient.
But managing that data history requires efficient indexing. And PostgreSQL 18 introduces a mechanical feature called skip scan for multi-column B-tree indexes.
A fantastic new feature.
How does this physically work to save database resources?
Well, traditionally, if you have an index on store location and product category, but you only want to search for a product category.
The database can't use the index efficiently, right?
Exactly, it has to read the underlying table. But skip scan changes this mechanical behavior completely.
How so?
It allows the database to physically jump over the B-tree nodes of the first column, skipping the store locations entirely to just find the product categories.
Oh, wow. That must save massive amounts of disk reads.
Huge amounts. And you can combine this with covering indexes, where the index itself contains all the data the query requested.
Completely eliminating the need to read the underlying database table at all.
I got it.
Incredible. But maintaining that performance requires rigorous monitoring.
Absolutely.
We have tools like pgstat statements for deep query analysis and pgbadger for parsing millions of log lines. However, the text specifically emphasizes identifying table bloat using pgstatus or tibbles.
Yes, table bloat is a silent killer of performance.
I understand that PostgreSQL uses multi-version concurrency control, meaning an update creates a new row and leaves the old one behind as a dead tuple.
Right.
How does table bloat physically impact the system if it's left unchecked?
Well, if the automated vacuum process does not clean those dead tuples, the physical file size of the table expands unnecessarily.
It just gets physically larger on the disk.
Exactly. And when the database performs a sequential scan, it must read all those dead, invisible rows from the physical disk, wasting massive amounts of memory and processing power.
So monitoring table bloat ensure your hardware resources are spent reading active data, not discarded history.
Precisely. It's essential maintenance.
Okay, so raw transactional data is perfectly safe when monitored, but it is useless if a business cannot read it to make decisions.
Very true.
Transforming data for analytics is our next focus. We are shifting from traditional extract, transform, load processes to extract, load, transform processes, doing the heavy lifting inside PostgreSQL.
Right. The ELT model.
I have a specific practical question regarding these transformations.
Sure, go ahead.
When should an architect accept the stale data of a materialized view over the real-time but write-heavy overhead of a table and trigger approach?
That's a classic architectural dilemma. The decision relies entirely on physical disk input and output costs. You should choose a materialized view when the dataset is exceptionally large and business users only require, say, hourly summaries.
Because materialized views pre-calculate the answers.
Right. They provide excellent read performance, but they offer stale data between scheduled refreshes.
And the alternative.
Conversely, you should choose the table and trigger approach when the business demands near real-time analytics, like live inventory tracking.
Because a trigger updates the analytical data instantly.
Yes, but every transaction fires a secondary update sequence on the disk. This imposes a significant write-heavy overhead on the server.
I see. It's a trade-off between read speed and write costs.
Always.
Transforming data allows us to transition away from complex data vaults, which require really slow table joins, into highly performant star schemas.
Yes, star schemas are much faster for querying.
Because a star schema denormalizes the data, placing facts in the center and dimensions on the edges. And once the data sits in a star schema, we can use window functions, CUBE, and rollup to generate complex summaries instantly.
You can even use recursive common table expressions to map hierarchical data.
Right. However, analyzing structured numbers is only one part of the equation. We must also analyze text.
The messy human data.
Exactly. How does the pgvector extension physically measure the statistical similarity between misspelled words?
The pgvector extension provides fuzzy matching by breaking words into three-letter groups.
Oh, and those are called trigrams.
Yes, trigrams.
Yeah.
If a user types a misspelled word, the database breaks the user's input into trigrams and compares them against the trigrams of the correct words in the database.
I see.
It calculates the percentage of overlapping three-letter groups.
That's fascinating. This mechanical comparison allows the database to handle user spelling errors automatically without requiring exact syntactical matches.
Exactly. It's incredibly robust.
But syntactical search is powerful for finding misspelled words, but it cannot understand actual meaning.
No, it just compares letters.
Right, a syntactical search does not know what a clothing item actually is. To analyze meaning, we must transition to the artificial intelligence capabilities of PostgreSQL.
The really cutting-edge stuff.
Yeah. We can describe an artificial intelligence vector as a mathematical fingerprint.
That's a perfect way to visualize it.
This fingerprint knows that a striped shirt is conceptually closer to a sweater than it is to a blender, even if the text descriptions share absolutely no common words.
Because vectors map semantic meaning into a physical location within a multidimensional space.
Right. And to manage these mathematical fingerprints, PostgreSQL utilizes the pgvector extension.
Yes, it's a game changer.
Large language models generate vectors with up to 1,536 dimensions. Without an index, the database must compare your search vector against every single vector in the database, which is computationally impossible.
It would take forever.
Which brings us to the IVF-flat and HNSW indexing methods. Now, I am slightly lost on the IVF-flat indexing. If we compare IVF-flat to a supermarket index, what exactly is the probe in that analogy?
Okay, in the supermarket analogy, the entire store is divided into localized zones, such as the dairy aisle or the bakery.
Okay, I follow.
Those zones are the clusters or lists created by the IVF-flat index. When you execute a search, you do not want to walk down every single aisle.
Right, that defeats the purpose of an index.
Exactly. The probe is the specific instruction you give the database, telling it exactly how many localized zones to check.
Oh, I see.
If you set the probe to 2, the database only looks in the 2 zones that most closely match your target vector, ignoring the rest of the store entirely.
That clarifies the mechanism perfectly. Alternatively, we can compare the HNSW index to a citymap index,
Yes, HNSW builds a complex, multi-layered graph of connections.
allowing you to navigate very quickly from broad highways down to specific neighborhood streets. The HNSW index provides exceptional speed and accuracy, making it the preferred choice for real-time applications.
It's generally the go-to for production AI.
However, the true breakthrough here is multimodal reasoning.
Absolutely. This is the core of the unified platform.
This involves combining semantic vector distance operators with standard SQL filters in a single query. Why is querying an external vector database so inefficient compared to multimodal reasoning within PostgreSQL?
Well, when embeddings live in an external database, you must fetch the semantic matches over the network, bring them back to the application, and then query your relational database to see if those items are actually in stock.
That sounds like a lot of back and forth.
It is. You might fetch 100 semantic matches over the network, only to discover that 99 of them are out of stock in your transactional database.
Which wastes time, network bandwidth, and computational power.
Exactly. By keeping the vectors and the SQL filters in the same PostgreSQL engine, the query planner prunes the data instantly.
Oh, so it calculates the Euclidean distance for the semantic match while simultaneously enforcing the structured business rules.
Yes, it filters by inventory and price at the exact same time it searches for meaning.
This ensures you never recommend an out-of-stock item again, solving our blue sweater problem. Now, Understanding how to query vectors is the theory, but we must operationalize this into robust production pipelines.
Theory into practice.
Right. You can integrate large language models, such as OpenAI, directly within the database using procedural languages like PL/Python to generate embeddings automatically.
Which is incredibly powerful.
However, calling an external language model takes time. Why does the architecture dictate an asynchronous approach for generating these embeddings?
Well, if you attempt to generate an embedding synchronously during a database transaction, you will severely impact the system.
Because it waits for the response.
Right. The database would lock the product row, send the text over the internet to the language model, wait for the mathematical vector to return, and then unlock the row.
And if the internet connection is slow, your entire checkout system halts.
Exactly. Your transactions pile up. Therefore, a database trigger simply writes a brief notice into a job queue table indicating a product description changed.
And then what happens?
A background worker process reads that queue, fetches the embedding from the language model independently, and updates the row later.
I see. This completely protects the operational integrity of your transactional system.
Exactly. It's safe and non-blocking.
We must also address the challenge of semantic drift. When you upgrade your artificial intelligence model to a newer version, the new mathematical fingerprints will not align with the old fingerprints.
No, they're entirely different dimensional spaces.
Right. You cannot compare a vector generated by an older model with a vector generated by a newer model. Therefore, you must strictly version your embeddings within the database tables.
Data governance is essential here.
Finally, we must explore the architecture of a Model Context Protocol Artificial Intelligence Assistant.
The MCP.
Yes. The database executes hybrid queries, retrieving semantic matches and applying strict SQL filters, and then returns factual rows of data to the language model. How does this architecture fundamentally reverse the standard artificial intelligence dynamic?
It reverses the dynamic by removing the language model's authority.
Oh, really?
Yes. In standard applications, the language model attempts to answer questions based on its internal training data, which, often leads to hallucinations and incorrect facts.
Right, the AI just makes things up.
Exactly. The Model Context Protocol establishes a formal contract where the database is the absolute authority.
Okay.
The database exposes tools that have strict inputs, explicit row limits, and rigorous safety checks. The language model merely translates the user's question into a query, but the database executes it.
This means the language model merely acts as a narrator of the retrieved data.
Precisely. A narrator, not a source of truth.
If the database returns 0 rows regarding a specific product, the language model is forced to narrate to the user that the product does not exist. It cannot invent an answer.
Because it has no external data to draw from.
This merges the conversational reasoning capabilities of modern artificial intelligence with the mathematical certainty of the relational database.
It's the most secure way to build AI apps today. Organizations that fragment their data across multiple specialty systems will face escalating costs and severe governance failures.
Because they are constantly moving data around.
Right. They will spend their engineering resources building brittle integration pipelines rather than building actual features for their customers.
While organizations that consolidate their meaning, their text, and their mathematics into a unified relational architecture will innovate faster and far more securely.
The database really regains its position as the ultimate arbiter of truth in the modern technology landscape.
That is a powerful conclusion. We conclude this comprehensive analysis with a forward-looking thought.
Let's hear it.
As artificial intelligence models become highly commoditized and easily interchangeable, the true competitive advantage for enterprises will no longer be the artificial intelligence model itself.
It makes sense. The models are everywhere now.
Exactly. Rather, the ultimate advantage will be the unified, governed, and multimodal data platform that grounds the artificial intelligence in absolute relational truth.
It all comes back to the data.
It does. This shifts the balance of power back to robust database architecture, a concept you must ponder as you design your future systems.
Sound advice.
We strongly recommend that you read the actual book, AI Ready PostgreSQL 18. To all of you listening, as friends of the show, we encourage you to subscribe to the program. We wish you a great day.